And Kevin, help me with the MO diagram. Who would like to do that? Yes? Okay, what's your name? Mega. Okay, think of an atom in your head that's between boron and neon. Okay, you got one? Okay, she has the atom, it's gonna be a diatomic. Tell your neighbors so they know it's a real atom. Is that a real atom between boron and neon? Okay. So think of a charge, okay? So +1, -1, something like that, okay? All right, we don't know what Mega is thinking about, so I'll just call it X2, okay? You don't even need to know what it is. We can draw the MO diagram, okay? So we can do some mind reading tonight. Draw the energy scale on the y-axis. Since I know it's in the 2Ps, I know there'll be a 2S energy level and a 2P. 3 lines for 2P because there's 3 2P orbitals. By the way, losers in the way back out there, you can come up here if you want to. Sit all around. There's a cool chair right there. Totally fine. And it won't bother me at all. Okay. In the back for review sessions. Okay, so I already know all this is true. For the 2S, remember the main concept, every bond has 2 parts, the lower energy bonding and the higher energy anti-bonding. Okay? We connect these with dots to make it look beautiful. Okay, the lower energy would be a sigma 2S because it came from 2S. The higher one is a sigma star, star meaning the anti-bonding or the higher energy, 2S. Okay, Mega, without telling me what the atom is, okay, don't reveal yet. Okay, I need to know if it's nitrogen or to the left, or I need to know is it oxygen or to the right. Which category does it fit in? To the right-hand side. Since I know it's on the right-hand side, I automatically know the picture is 1, 2, 2, 1. Something from your reader and textbook to be aware of. So again, connect the dots. Okay. Hi, welcome. Yeah. Okay. So, good mnemonic to remember when you see one line by itself, it's always called a sigma. When you see 2 lines together, that's always a pi. So it's an easy way to remember which one's which. I don't have time tonight to go into why that's true. So sigma, pi, pi, sigma. Just based on the number of horizontal lines next to each other. That's why these 2 are sigma. Subscript is always where it came from, so all these are subscripted to P. 2P and 2P. The lower energies are the bonding, the higher energies are anti-bonding, so both higher ones have a star next to it, meaning anti-bonding. Okay, I have now successfully came up with her MO diagram, all without knowing what the atom was. So now I'm just going to finish the very last part, which is put in the electrons, and it's time to reveal the atoms. What element were you thinking of? Oxygen. So really, we'll change colors here. This was oxygen. And what charge were you thinking of? Be positive, negative, -1, -2, -2, okay? So she was thinking of that, okay? There's 2 ways to draw this, but as far as I'm concerned, it's O2 minus, so it doesn't matter how you break up that minus charge, but you need to have that 2 minus somewhere. So you could put O and O2 minus, you could put O minus and O minus, you could put O2 minus and a neutral oxygen here. So I'm just going to do this. Doesn't matter to me. Might matter to dope doctors. Okay? All right. So now I write the electron configuration. 1s2, 2s2, 2p4. This is 1s2, 2s2, 2p6. Okay, so that's just electron configuration. Notice I'm going to fill in the parts I just underlined, the 2s and the 2p for my electrons. So let's do that in purple. So this is 2s2, 2p4. Has to be filled in like this. Okay, 2s2, 2p6, everything would be paired for that one. Like that. Okay, and then now we do one diagram at a time. So let's start with the lower one. There's 2 on each side for a total of 4. 1, 2, 3, 4. Okay, now we go to the upper diagram. There's 4 on the left, 6 on the right, total of 10. It has to be filled out this way. 1 and then paired 2. 3 and 4 are unpaired. Then 5, 6 are paired. 7, 8 are unpaired at first, and then 9, 10 they're paired. Okay, so now I have all 10 in the middle. Now, I look only at the center part of the diagram to determine the magnetism. So in the center, what's the magnetism? Yeah, it's diamagnetic. You know that because they're all paired. Okay, second thing that we commonly ask you is the bond order. Okay, it's something minus something divided by 2. What's the first something? Yeah, you go 6. It's a number of electrons in bonding molecular orbitals. I recommend just looking at the uppermost diagram. It's easiest. So 6, do 4, 6 in bonding with no stars. What's the next number? 4, the number of electrons in anti-bonding molecular orbitals, and 2, 4. So that's 2 over 2. That'd be a 1, single bond. Okay? Did I miss something? No. Looks good to me. Okay? All right. So this is something you couldn't draw with Lewis, but you can have an MO diagram for it. You'd be done. This is probably on the final. I forgot what it was on the final, but it's usually at least a 20-point problem just to do that. Okay? So I personally, it doesn't get harder than this. I would hope there is one, and there is. Remember, I guess if you're in my class, I have that final review worksheet, so I have the list of everything to study. So you should have your 4 finals posted, which everybody has posted. If you have my practice exam, you have an extra final, and then extra 130 extra questions for fun. But there's also this, which I made, which has about 25 questions or so. So if it was me, the order I would do it is this and the 4 practice finals. If you have enough time to move on to the sample questions and the 2004 final in the back of my practice exam. So that's the order I would do it, if I were you. Okay, here's a Lewis structure problem. This I would consider a fairly tough one. Okay? So let's try this one. I5 minus. I'll start with the valence electrons. Okay? 5 iodines in column 7 plus a 1 because it's a minus 1 charge, so 36. Now, I'm drawing it all linear instead of an iodine in the center and 4 other iodines around it. Why am I drawing this linear like this in kind of a line sort of fashion? Because it says it's V-shaped. So I would not draw this. I'll draw this on scratch. I would not do this. There's no way this would ever look like a V. Okay, so don't be ridiculous. It says V. So don't draw something like that. Normally you would draw something like that, except it gave you additional information. Okay? All right, so this is what we got. It's 2, 4, 6, 8 of 36. Now I go to the terminal, or the external atom. So let's see, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So now I'm at 20 of 36. Now I move my weight inward. 20, 22, 24, 26, 28, 30, 32. So now I'm at 32 of 36. I have 4 more electrons to go. Where do you want to put those 4 electrons? Let's call them number 1, 2, 3, 4, or 5. 3. You want to put them on 3, okay? Let's put them in a, because now we're kind of unsure. There's 3 central atoms, so there's 3 choices. You could put them here, that's fine. Okay? Now, let's next go to shape, because we want to make sure we get to the V. Okay? All right. So we're going to consider the shape of these 3 in the middle. Let's start here. What's the electronic geometry of that one? You see 4 groups, so it's tetrahedral. 2 are lone pairs, so we call it the molecular geometry bent. Same for number 4. Okay, so what's the ideal bond angle? 109.5. Will this look like a V? In no universe will this look like a V if these 2 are bent. Does that make sense? This one should be the bent one, these should be straight. Okay. Good idea, but bad idea. You know what I mean? Okay. All right, where do you want to put those? Yeah, we're going to try 2 and 4 to make it symmetrical looking. All right, let's see if this is a bad idea. Okay, here we go again. That one right there, what's the electronic geometry? You see 5 groups, it's called trigonal bipyramidal. 3 are lone pairs, and thus, what's the molecular geometry is? Linear. That's good. That's what we were hoping for. What's the bond angle? 180. Yeah, it has to be. It's linear. This one is identical to this one, so 2 and 4 are the same. Let's do this one again. Electronic geometry. Tetrahedral. Molecular geometry. Bent. It's 109.5. I think we have a V, so we have a winner. You would redraw it if they wanted you to draw the correct shape. So if at first you don't get the correct Lewis structure, just try something else, like we did here. Because this species is charged, you can put brackets around it and a minus right there. Okay, we did all the shapes, we did all the bond angles, it looks like a V. Now let's work on hybridization. We were asked about hybridization a little bit earlier. Let's get a different color. This one. What's hybridization? S, P what? And? Yeah, these are both S, P, 3, D. This one is S, P, 3. Remember the little table I taught you? Hybridization in groups. If the groups, they count down 1, 2, 3, 4, 5, 6. From VSEPR, hybridization is S, SP, SP2, SP3, SP3D, SP3D2. So once you max out on the P's being 3 at 4 groups, you need to start adding D's. So it's pretty simple. This is something that if you think you're going to forget, to write on the final right when you start and refer back to it later. Okay, let's also do a polarity. Polar, non-polar. Definitely polar. It's asymmetric. At least that's not the way I taught in my class. How many pi bonds? 0. How many sigma bonds? 4. 1, 2, 3, 4. Remember, every bond has a sigma. Okay, I think we did about everything. Oh, let's do formal charge. Yeah. Oh my God. Formal charge right there. 0. Right here. Looks like a -1, and here. Positive. And zeros. Yep. Do I need to review how to count formal charge? You good? Good. Okay. I heard more good, so. All right. So there we go. That would be a pretty full sort of question. What do you want to make a double bond? Here? Taking one lone pair. Is it one of these or one of these? On the right? So you don't want to do this. Don't do this yet, everybody. Okay. You want to do that? There's a problem. What's the problem if I do that? It's okay if I break the octet. It's fine. This has how many groups now? 4. And that makes it bent. And that doesn't fit the V shape. But otherwise, nice idea. Yeah, but because that would fix the formal charge, is probably what you're thinking. You're right. But it would undo the question. Yeah. Did you want to, yes? Why did I put my electron pairs here? Here? These electron pairs, it doesn't matter where you put them. They're actually going in and out of the plane. So this is right at black. It can't be properly represented. Okay. Oh, yes. Hello. Why is it polar? It's polar because it's asymmetric. A symmetric shape would look like an X, where there'd be iodines down here. Yeah, but this is a B. It has one line of symmetry, but not this line of symmetry. That's a problem. Okay, I have a question. Did you want to do something else where we count sigma and pi bonds and do hybridization? Yes or no? Okay, I'll do it quickly. Let's try this. Okay. All right. I'm going to give you let's do hybridization first. What's the hybridization right there? SP what? SP2. Because there's 3 groups. Remember, the hydrogen is not drawn in. Right? There's extra hydrogen right there because every carbon has how many bonds? 4. Okay. So this is sp2. All of these carbons around the ring are sp2. Okay, how about that carbon right there? sp2 also, same with that carbon. All right, now let's have more fun. How about this one right there, that carbon? sp3. There's 4 groups, so it's sp3. I'm referring again to this table that I made earlier for you. Okay, this oxygen. sp3. Because there's how many groups? 4. Where are the mystery 2 groups? Yeah, they're lone pairs. You should have known that. oxygen, if it has a zero formal charge, has 2 lone pairs. If your instructor didn't tell you that, I guess they assume you already knew it, so they didn't have to tell you. Okay, I'll give you a head start on me and count the sigma and pi bonds. I'll write my answer off screen. Okay, I'm ready. How many pi bonds? I got 5. Okay. Sigma bonds, did people get above 15? Yes. Okay. Did you get above 20? Yes. Okay, what'd you get? Wow, you got really high. Okay. Let me count. I'll mark it as I count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. I think that's everything. Yeah. Structures is the oxidation state. Because that was chapter 3, I just want to quickly punt to that. Okay, so we could ask you, for example, what's the oxidation state of xenon? You would say, not 0. Plus 2, because fluorine's minus 1. Let's just try one more for fun. Chlorine. Not minus 1. Plus 5, yeah, because oxygen's minus 2, hydrogen's plus 1. So it looks like it's plus 5. So make sure you can still do that. I know it's way back in chapter 3, but we like to combo those Lewis structures with oxidation states. Okay? Alright. Let's do this stuff, the trends, all that. Okay, 2 things I want to say about that. One is for my reader. I'm going to go to chapter 8. You want to know this table on page 89. These are all the trends you need to know. Okay? So it generally follows this trend where electronegativity, ionization energy, electron affinity, and the effective increase to the right and up. Shielding radius, screening, metallic character increase to the left and down. There was, should have been for your classes, we showed you some exceptions specifically to the ionization energy. And I don't know how the other instructors taught it, but when I did it like this. I showed you a table like that, okay? And I asked you, see the ones highlighted in green? Why are the green ones so large? Raise your hand if you know, one person. Yeah, right there. Because on those, you're moving an electron from a core electron space. So sodium, the first ionization energy takes it to neon, But the second one is so huge because you're going away from the noble gas configuration. I also showed something like this. Let me show you another one. I'll show you this one, I guess. The sulfur, that one is highlighted. It's a little smaller than expected. Somebody raise your hand and tell me why that's true. Yeah?
It has a 3p4 or 2p4.
You got it, yeah. So sulfur, remember another concept, I'll write both of these down in a second. When you get to a half-filled shell, so 3 out of the 6 of the p orbitals, that's a very stable situation. So it's lower energy than what you would expect. So the two concepts from there that you'd want to think about, just really for ionization energy is what we highlight in our class, or I mean Chem 2A, is point one. A full shell is stable. That means low energy. A full shell would mean like all the 2p6 or 3s2, where the s's has 2 or the p's have 6 or the d's have 10, etc. A full shell is stable. That's because of the noble gas configuration. And even if it's not a noble gas, it's still stable. The second is a half shell is stable, i.e. that means low energy, and that's because of the pairing energy. So like a 2s1, that's stable, it's half filled, or a 4s1, or a 3d5, 5 of 10, or a 4p3, 3 of 6. So when it's halfway filled, that's also stable, so lower energy than what you usually expect. And when we say energy here, we're talking about ionization energy, okay? All right, cool. That's all I have for trends. If it's not this, then just know the trend table, okay? Okay, let's move on. What's the hybridization of that nitrogen? sp2. We could ask you to draw the hybridization scheme. That's one thing I forgot to do. So, what you would do on the left-hand side, you'd probably draw the normal or unhybridized nitrogen, which is, let's write the configuration 1s2, 2s2, 2p what? 3. So you go 2s, 2p, 1, 2 for 2s2, and 3 for 2p3. On the right-hand side, I'll do that in a different color. I'll do it in brown. We hybridize it, so this would be the hybridized nitrogen. From here, from the molecule, you know it's sp2. So you're going to draw this sp2 hybridization scheme. So you draw your normal sp2 hybridization scheme, which is this. 3 lines for 3 sp2 hybridized orbitals, and 1 2p unhybridized orbital. Okay? In your class, you should have done this for carbon, where you drew an unhybridized carbon, which is 2s2, 2p2. Okay? Then you should have learned 3 hybridization schemes for that carbon. SP, sp2, and sp3, which are here. Don't totally fit on the page. You don't really have to worry about these pictures here on the right. Don't worry about the pictures on the right. But I redrew the sp2 in the middle. See that one? That's because I knew that nitrogen in my molecule had 3 groups, so it's sp2. If I calculate sp3, I draw the top picture. 3 lines, 4 lines, all at the same level. If I figured out it was sp because there's 2 groups, I would draw this bottom picture. That's it. Is that okay? That's how I do it. So you have to know that schema of all 3 of those. I assume everybody learned this? Wow, what class did it? In? Yeah, for sure. Hayashi? Kumakar? No matter how many electrons there are, okay? It's going to take one of them in the 2p. The sp2, or the hybridized orbitals, whatever's left over, takes the rest. So there's a total of 5. 1 is here, so I'm going to put 4 in here. So just like this, 1, 2, 3, 4. See how that works? That's it? Okay. Now, see this right here? That right there, these two. Look up at the original molecule. Do you see where these are? Yeah, that is, I need another pen, those two. Those two are those two, okay? Same ones. Okay. These two here, let's do this one. This one, okay, that one there, where is that in the picture up above? Yeah, it's the pi bond of the double bond. Okay? So it's the second bond of the double bond. Not the first one, but the second one. That's a pi bond. Okay. These two folios are where? Yeah, they're the single bond and the first of the two bonds of the double bond. Okay? Or if I would say it in another way, the hybridized orbitals, that's these, the hybridized orbitals all form sigma bonds. So those are the single bonds, or any bond has a sigma. And the two p's all form the pi bonds. So if you don't know the little summary, it goes like this. Bond. This is scratch kind of right here. This is not part of the picture, okay? Okay. Single, double, triple. Sigma, pi. Okay. Single has how many sigmas? Pi's? Yep. This? 1. Yeah. This? Yeah. There we go. So the first bond of every bond is a sigma. Any additional bonds are pi's. So a double bond has 1 pi, triple bond 2 pi's. Okay, so I forgot to do one of these, but that's how it works.
Question.
Yeah.
Are we allowed to, do we have to know how to draw the hybridization for the 2O?
For oxygen? Well, okay, let me put this picture back up. Okay, this picture here, this works for any atom. And for us, that would be like a carbon, a nitrogen, or like a fluorine. You use the same scheme. The only thing that changes is, number of electrons. So let me do an example since you asked, really quick. This will be the last thing I have time to do, unfortunately. If you have this, what's the hybridization? 3 for oxygen. So if I go back to this picture, I'm going to draw the sp3. See that?
My question is, do you have to know how to draw the hybridization for like not the central atom.
Oh, I see what you mean. No, if you have a non-central atom, what do? Most people consider it unhybridized, so it would be 2 P's. If it's unhybridized, it'd be 2 P's. There's no hybridization. Yeah. Oh, so then do you still want me to finish this? Okay. So you go unhybridized on the left, 2s, 2p. For oxygen, it's 2s2, 2p4. So 2s2, 2p1, 2, 3, 4. You'd hybridize this. In this case, I know it's sp3, so I'm going to draw that. And I have all my electrons here. That's 1, 2, 3, 4, 5, 6. So that's 1, 2, 3, 4, 5, 6. And then if I ask you, these electrons are where? Yeah, the lone pairs. See how the pairs? I mean, where else could it be? And then these two, sigma bonding to the hydrogens. These represent the electrons going to the hydrogens. Okay, see how that works? Doesn't matter what the atom is. All right, here's what we're going to do. In a moment, I'll dismiss you. Don't knock my camera over when you run out. And then for the next half hour, people want to say, I'm going to do specific questions. So you raise your hand. So I do this question, I'll answer, okay? But how was this in general? Helpful? Yeah.